Chapter 5.1 looks at electron configuration, which is something that we looked at a lot at GCSE. And it just refers to how electrons are arranged within an atom. So for example, if I were to look at lithium, lithium has a mass number of 7 and an atomic number of 3. The atomic number I look at when I want to know the number of electrons. So it tells me lithium has 3 electrons. And if I were to draw lithium, I would put 2 of those electrons into the first shell, and then I would move to the second shell for that third electron. And I could write this as just 2, 1 for the electron configuration of lithium. If I look at sodium, the numbers are 23 and 11. 11 is my atomic number. It tells me how many electrons I've got. And I would put 2 electrons in the first shell. I would put 8 electrons in the second shell. And then I would need to move on to the third shell for that final electron. If I were to draw calcium, which is the biggest element you would have been asked to draw at GCSE, I've got 20 electrons to assign. I'm going to put 2 electrons in the first shell. I'm going to put 8 electrons in the second shell. 2 and 8 is 10, so I've got another 10 electrons to go. I'm going to put another 8 electrons into my third shell, and then I'll need to draw a fourth shell for the final 2 electrons, and I would write that as 2, 8, 8, 2. If you look at the periodic table, you will see that there's a relationship between the electron configuration and where the elements are actually located on your periodic table. So I've got lithium and sodium that are both in group 1, and you can see from my diagrams that both lithium and sodium have got 1 electron in their outer shell. Okay. In general, you can say that if elements are in the same group, they will have the same number of electrons in their outer shell. So nitrogen and phosphorus will both have 5 electrons, fluorine and chlorine will both have 7. You can also use your periodic table to see how many electron shells you will actually need to draw to fit all of the electrons in. So for example, with hydrogen and with helium, hydrogen's only got 1 electron, helium's got 2. So their electrons will fit in just 1 shell. So you only need to draw 1 shell for the period 1 elements. If I move down to period 2, all of these period 2 elements will require 2 electron shells. In period 3, you'll need 3. In period 4, you'll need 4. And you can see that from my diagram. Lithium's in period 2, I needed 2 shells. Sodium's in period 3, I needed 3 shells. Calcium's in period 4, I needed 4 shells. We never asked you to draw anything bigger than calcium at GCSE, and there is a reason for that. If you were to try and draw bromine, okay, looking at my periodic table, I know bromine's in period 1, 2, 3, 4, so I know it's got 4 shells, and I know it must have 7 electrons in its outer shell. But if I try to actually draw, I'm not going to draw bromine, I'm just going to write the electron configuration. So it's got 35 electrons in total. In the first shell, I would put 2. In the second shell, I would put 8. In the third shell, I would put 8, just as I did for calcium. And then I would move into the fourth shell, and I would still have 17 electrons to go. I know I can't have a fifth shell because bromine's in period 4, yet I know that bromine has to have 7 electrons in its outer shell to be in group 7. So, following the rules I've always used at GCSE, I run into difficulties when I go past elements that are bigger than calcium, and bromine is a prime example of that. So what we need at A level is a more complete model. This model worked fine for GCSE, but it has limitations and it's not going to work at A level. So at A level, we are going to use a different model of atomic structure, and we are going to use the orbital model of atomic structure. So if I look at the definition of an orbital, you can see that the idea of orbitals is generally the same as the idea of electron shells that you have become familiar with at GCSE. So if I look at the actual definition for an orbital, which I have for you here, an orbital is a region around the nucleus which can hold up to 2 electrons with opposite spins. Now we'll come back to this opposite spins point later. But in general, you can simplify this definition down to just saying an orbital is the space around the nucleus where you will find an electron, which is A similar idea to what we had with shells, okay? A shell was the area around the nucleus where you found electrons. An orbital is now that space around the nucleus where you are going to find electrons. And if we look at the orbital model, I'm going to come down here and I'm going to do it just for hydrogen first. Hydrogen only has one electron. So if I draw this little black dot here in the center to be my nucleus, okay? If I were to draw this, the GCSE model, I would draw my hydrogen in the center and I would draw one electron in the first shell surrounding hydrogen. When I draw this using the orbital model, what I'm going to do is instead of putting that electron in a shell around the hydrogen nucleus, in the orbital model, I don't actually know exactly where that electron is going to be. Okay, that electron could be here, or that electron could be here, or it could be here, or here, or here, or here, or here, or here, or here. The point is, this electron, it's only got one electron, by the way. All of these dots are representing the same electron, but that electron is moving. It doesn't stay in the same place, and I don't know exactly where it is. It could be in any of these places, and you can map the locations of an electron in an atom. And when you do this for hydrogen, you see that that one electron moves around all over the place. And you come up with a diagram that looks like this. Okay, so this is the hydrogen nuclei. Each red dot represents that same electron. Hydrogen only has one, so it's the same electron. But that electron is moving all over the place. But what you will see when you look at all of the different places that that one electron has been is that it is confined to a certain area. And that area you will see is in a circular shape. Now, because atoms are 3D, they are not 2D, instead of describing this space as circular, we're going to describe this space as spherical. So what I've just drawn here, all of these red dots, that represents an orbital, because an orbital is just the space around the nucleus where you're going to find an electron. And because this orbital is spherical in shape, I'm going to say that it's an s orbital. Okay? If I look back at my GCSE model, I would say that this is the first shell. So when I'm using my orbital model, I'm going to say that this is the 1s orbital. Okay? The 1 is equivalent to the first shell, which we had at GCSE. And if I were to do something similar for helium, helium has got 2 electrons. So I'm going to draw my nucleus in the center. I'm going to do my GCSE model. I would draw helium and I would draw 2 electrons in the shell surrounding the helium nucleus. For my orbital model, okay, I've got 2 electrons to draw, so I'm going to use 2 different colors. But the point is that one electron could be here, or here, or here, or here, or here. It could basically be anywhere within this set space. That's for one electron. Remember that same electron is just moving. And then helium's got a second electron, which could also be pretty much anywhere within this spherical space. Okay, so this whole region where you can find an electron is called an orbital. This region is spherical, so I say it's an s orbital. And this s orbital is equivalent to the first shell that we had at GCSE. So I'm going to say it's a 1s orbital. Now, if I go back to the definition that I gave you for orbitals a second ago, you will see that orbitals can only hold 2 electrons. So far, we've looked at hydrogen and helium. This hasn't been a problem. But when we go on to look at lithium, you will see that lithium has got 3 electrons. But an orbital can only hold 2. Okay, we encountered this problem at GCSE. Okay, the first shell could only hold 2. So what did we do? We moved into a second shell. If your orbital can only hold 2 electrons and that orbital is full, then you just need another orbital to take on the third electron. And that's what's going to happen with lithium. With lithium, you are going to need another s orbital. Again, I'm calling it an s orbital because it's spherical in shape. But instead of calling it a 1s, because it's equivalent to the second shell at GCSE, I am calling it a 2s orbital. And remember, these structures are all 3D. So this model here is slightly more accurate. I've got my 1s orbital, which is a 3D sphere. Then you move into your 2s orbital. So you have another sphere that's going to surround your 1s orbital. So for lithium, the first 2 electrons in lithium will exist in this 1s orbital. And then in the second orbital, the 2s orbital, lithium's third electron will be moving around this space here. In between the 1s, which I've got in yellow, and the 2s orbital, you will see that there is a gap. This gap is called a node, and it's just the space between orbitals where electrons cannot exist. If you had more electrons, you can have more orbitals. So here I've got a picture of a 3s orbital. Okay, this 3s, S because it's another spherical orbital, 3 because it's representative of the third shell. Now, if we go back to our GCSE model, you will see that we had 2 electrons in the first shell, that's fine. But in the second shell, we have got 8 electrons. In my 2s orbital, I can only hold 2 electrons. And then in my s orbitals, I'm jumping up to the third shell. What about the other 6 electrons that we were able to get into the second shell at GCSE? If I can only put 2 electrons in my 2s orbital, where are my other second shell electrons going? For that, we are going to need a p orbital, which I'm going to go through on the next video.